Hey, ChemExcel. Right. Today we're going to look at some Hess's Law puzzles. All right. I call them puzzles because that's basically what they are. All right. You're given some pieces and you have to see how they fit together and manipulate them to help make them fit together. Okay. All right. There we go. All right. So the goal of Hess's Law puzzles is to make two or more given equations add up to create a specific equation. Then you can add the delta H values of the given equations to find the delta H value of that specific equation. You may have to modify the delta H values before they can be added together. So in example 1 here, we want to find the delta H of reaction for the reaction of A to D. So that's the specific one, all right, that we're looking for. Here are the given equations. Okay, we have A turns into B with a delta H of plus 30, so that's endothermic as a little review, right? Takes in heat. And then we have B to D with a delta H of plus 60. All right, this one's pretty straightforward because these equations, if we just add up the equations, we've got B on each side, so it's kind of like algebra, you have X on each side, the equal sign. We've got B on each side, those will cancel, and we are left with A to D. That means we can just add these values up. 30 plus 60 gives us 90 kilojoules. Okay? All right, now let's start manipulating some reactions. All right, in this one, we're looking for the reaction X to Z. And if we look at what we've been given, we have X to Y and Z to Y. All right, so I've got my special science helpers here who are going to kind of help give the thought process for this also. All right, Philip and Michaela, we need X to be on this side of the arrow. So where do you see X? Do you see X in equation 1 or equation 2?
I see X in equation 1.
Okay. And which side of the arrow is it on? Is it on the correct side already?
X is on the correct side already.
Okay. So this is the only place X shows up. All right. And it's already on the correct side. So we aren't going to do anything to equation 1. We're just going to use as is. Okay. All right, we're going to say like leave as is. We don't want to mess with that because we need that X over there. All right, now we also need to get a Z in here, but we need it on the other side of the arrow. Michaela, which equation do you see a Z in? Do you see a Z in this first one, or do you see a Z in equation 2? You gotta say it out loud.
2.
2, okay. All right, now Michaela, if you look at this, we want Z to be on the right of the arrow. Is the Z on the right of the arrow?
No.
So what that means for this is that we're going to flip this equation. So rather than Z to Y, we're going to make it Y to Z. All right, but if we look at that delta H value, it started off as an endothermic reaction. If we run it backwards, it's going to be exothermic. So now our delta H is negative 95 kilojoules. So now we're ready to add these equations up. You can see that the Y's would cancel. We would get the equation we're looking for. All right, so we have 40 minus 95. Philip, do you know what 40 minus 95 is? Probably not, right? You want to type in the calculator? Do 40 minus 95.
Negative 55, everybody.
All right.
I was going to say that, actually.
Awesome. All right, so we have negative 55 kilojoules. All right, got 2 more examples just to show you a few more things. This is where it's going to get real. So we have actual equations, not the nonsense that we had in those first 2 examples.
No nonsense.
No nonsense.
No
All right,
nonsense.
so this is the equation that we're looking for up here. And this is a real reaction. N2 reacts with O2 and forms 2 NOs. All right, that really happens. All right. These are also real equations. So N2 can also react with some O2s to form NO2. All right, we've seen that nitrogen and oxygen can form many different compounds, those molecular compounds, right? You can also react nitrogen monoxide with oxygen as another way to get nitrogen dioxide there. Okay? So these are all real reactions that take place, and we know the delta H values of these 2 reactions. We'll go ahead and number them 1 and 2. Okay, so first thing we're just going to go through, we're going to locate these puzzle pieces, all right, in this big mess down here. So we need to find the N2. All right, Philip, do you see N2 anywhere?
Yeah,
What
I
is
do.
that?
First equation.
First
Right side of the arrow.
All right. On the right side of the arrow?
Yeah.
So N2 is over here?
Hmm.
No. Where's the N2?
All the way over there.
Point at it. Here. But is that N2?
No.
Does it look just like that?
No.
So we need to find N2's formula exactly like this. There we go. So now he's pointing over here. So there's our N2. Okay. All right. It's already on the side of the arrow we want it on.
Mm-hmm.
And it's in the correct quantity. We have one of it and we want one of it. So we're going to have to leave this as is, because if we mess with it, leave as it is. If we mess with it at all, that's going to mess with the N2. It's the only place it shows up. Now, if we move on to find the O2, we'll notice that O2 is in both of these, isn't it, kiddo?
Mm-hmm.
Yeah. All right, remember in balancing equations when I said that if something looked hard to balance, to just leave it to the end? We're going to do the same thing here. We're just going to move on, okay? And find that 2NO. All right, or at least let's look for NO. All right, Philip, where do you see NO?
I see NO here and NO here.
In here? So,
no here and no here.
Okay. Now, see that 2 after it, though?
Yeah, I don't know what it means.
Does this one have a 2 after it?
No.
Here? No. Okay. So these NO2s are not what we're looking for, because these are NO2s and we just want NO. All right. So keep looking. You seen NO anywhere else?
Right here.
Right here. And that's written exactly as NO. Okay. We have the right quantity. We have 2 NOs and we want 2 NOs. All right, but it's on the wrong side of the arrow, isn't it?
Yay.
Okay. So we're going to have to flip this around. So say 2 NO2s make 2NO plus O2, which means we got to flip the sign here, right? Mm-hmm. Because if this original reaction was exothermic, when we flip it around, it's going to be endothermic. So we have a positive there now. Okay. You want to cross it out next time? Okay. All right, so now if we add these reactions together, all right, we'll notice that the 2 NO2s are going to cancel out, which is good. We don't want them. They're not in this reaction up here that we started with. All right, we pull that N2 down. We have an N2. There's 2 oxygens over here and 1 on the other side. That's like having 2X on one side and X on the other. So that's going to end up just being an O2 over here. All right, so that one will cancel. And then on this side, we're left with the 2NO that we want. So we've made these equations, add to what we're looking for. So there's our calculator, dude. All right, so we can finally add these up as well. So if we do 67.6 plus 113.2, we get delta H equals 180.8 kilojoules. All right, for those of you who are thinking this is going to be really tedious, like crossing things out and rewriting things, it sounds like it's going to be tedious, but
it's not.
It's actually not, all right? Here's the thing. We didn't really need to rewrite this whole thing out, because if we leave the first one as it is, we would get the N2 exactly where we want it. Let me just get rid of some of this other stuff here. Okay. There we go. All right, if we leave the first one as it is, we have the N2 exactly as we want it, right? If we flip the second one, we have the 2 NOs exactly where we want them. And we can't mess with them in any other way, because if we mess with either equation in any other way, we won't get these 2 pieces of the puzzle where we need them. So we really just have to write over here, let's leave this as it is, let's flip this, maybe we turn it into that. All right, and this is really all your work would need to look like. Okay, so let's try that on this problem. All right, full out one. We've got 3 different reactions here. All right, multiple things that we can do with these. And we're going to see one more thing that we haven't done yet.
Ooh,
yeah.
Many equations.
Many equations. All right, so if we look here, first thing we want is 2 carbons. All right, so first let's just look for carbon. So we need to find a C that has no other letters attached to it. Do you see a C with no other letters attached to it?
Yeah.
Which equation is it in?
This one.
This one right here? Okay. So we do have a C. It's the only place we have C with no other letters attached to it. So we just want carbon, carbon. But what's the problem? We need 2 carbons here. Is that what we have in this equation?
No.
No. So in order to get those 2 carbons, we're going to have to double this equation.
Doubling.
So we're going to have to double the delta H value as well. Okay. All right. If we run the equation twice, all right, if we use twice as much of everything, we're going to produce, right, exothermic, we're going to produce twice as much energy. All right, so we've taken care of the 2 carbons. All right. How about H2? Do you see the H2 anywhere?
Yep.
Where's that?
H2 is right there.
H2 right here. Now, is the H2 completely by itself, or is it attached to another letter?
Oh, attached to more letters.
Another letter. Oh,
okay.
All right, then that's not what we're looking for. Here we go. Okay, so we have H2, H2. We already have the right number of H2s, don't we?
Mm-hmm.
Is it on the correct side of the arrow?
No.
Let's see. We want on this side of the arrow?
Okay, yeah, but it's in the wrong spot.
Okay, so as long as it's on the correct side of the arrow, it doesn't matter if it's in the first spot or the second spot.
Oh.
Okay. So we're going to have, this is the only place we have H2, so this is going to have to be leave it as is. All right, because if we mess with this equation at all, then we won't have that H2 where we want it. All right, last piece of the puzzle, we're looking for the C2H2.
G. And it's right
It's
here.
right here. Okay.
But it's on the wrong side of the arrow.
It is on the wrong side of the arrow. And do we have the right number of it?
No.
No. We only need 1, but this one has 2. So up here, we were able to multiply by 2. All right, what's the opposite of multiplication? What's the opposite of multiplication, dude?
Now we need to divide it by 2.
Divide it by 2, exactly. So we're going to have to divide this by 2. And we're going to have to flip it, all right? Flip, divide by 2. So our minus sign is going to have to become a plus sign when we flip it. Okay? So if you want to go through and rewrite the equations, all right, you can. All right, you're certainly welcome to do that. This one I would probably just squeeze the 2's in here. This second equation, you'd have to rewrite the whole thing. You'd have to cut it in half. You'd end up with like a 5 halves in there. All right, this one you leave as is, and then you could add them up. You could double check that everything that's supposed to cancel cancels, but it's also going to have to, because we have to do these specific things to these equations in order to get these little check marks up here.
Mm-hmm.
And if we do anything else, we can't get things where we want them in the right numbers.
Yep.
Okay, so this is all you really need for the work, is indicating like what are you doing to each of the equations, okay? And then most people feel better about actually doing this. So if we do negative 393.5 times, whoops, not divided by, times 2, we get the negative 787. All right, if we do 2598 divided by 2, we're going to get 1299. We're going to leave this one as is. So if we add all of that up, we've got negative 787 plus 1299 minus, right, this 285.8. And we get our delta H equals positive 226.2 kilojoules.
Cool.
Yeah. So the bottom line of Hess's Law Puzzles is don't focus on what you need to get rid of, focus on what you need to get. All right. And if you can figure out how you get what you need, all right, then everything else will work out just fine. All right. Say bye.
Bye.
Bye. Thanks for listening.